I'm not as bad as
Yeah.
I thought. I think I'm recording it now. I think so.
I just got pens.
You've just got?
A pen, as in I can write on what you're writing.
Oh,
I don't
real?
know
That's
how.
awesome. Okay,
Yeah, but
cool.
like I don't think it appears on anything else.
No,
but
it doesn't
mine.
appear on my screen, so I think it's only on your screen, so that's fine. Okay, good. Right, we're recording the meeting as far as I know. Hi, Kwesi, nice to see you as well. Let's get started again. Okay, so we were talking about the whole idea of derivatives. Now, derivatives when it comes to graph sketching specifically. So this whole idea is talking just about the applications of graphs. Is a first derivative talks about the gradient of the graph, and the second derivative talks about the concavity. So if the first derivative is positive, it means the gradient is positive, because remember, this is what we call the gradient function. So it indicates the gradient. And if the the first derivative is negative, we are looking at a decreasing function or a negative gradient. And then very important, we have these ones where we say at these points, these turning points, which we also refer to as our stationary points, the derivative is equal to 0. So very, very important. Turning points are stationary points because the graph is literally standing still. As you can see over here, the graph is a positive gradient. It's increasing, so it's going up, 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 up. Then it hits that 0 gradient, which is where we have our turning point or our stationary point. Then the graph is decreasing, so it's going down, 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 down. Then we have another stationary point, and then it's increasing again. So this is where our derivative, first derivative is 0 because we have a stationary point or we have a turning point. Now, concavity is looking at the second derivative. So if I find the derivative of the first derivative, I can then go and I can say graphs can either be concave down or they can be concave up. So when a graph is concave down, the second derivative is negative. So in this case, it's concave down, so the second derivative is negative. In this case, it's concave up, so the second derivative is positive. And this is one of the ways to determine whether a turning point is a maximum, a local maximum turning point or a local minimum turning point.
Yes.
Because at the same time here, the stationary point, the first derivative is 0, but the second derivative is negative because it's concave down. So at a local maximum turning point, the second derivative is negative. Whereas over here, at a local minimum turning point, it's concave up, which means at a local minimum turning point, the second derivative is positive. And then what we also have is we have these points of inflection. So a point of inflection looks like this. A point of inflection always in a cubic function, by the way, lies halfway between the two turning points. So if this is my first turning point and this is my second turning point, then literally halfway between the two. Say, for instance, this is 1 and this is 3. Then halfway between 1 and 3 is 2. So at 2, you have that point of inflection. And because of that point of inflection, the point of inflection is where the concavity changes from concave up to concave down. But this point specifically is where the second derivative is equal to 0. Okay, so second derivative equal to 0. Are there any AP Maths guys on this chat at the moment or not?
Used to be AP Maths.
Okay, no, it's fine.
No,
It's just for AP. No, it's just for AP Maths people. This isn't always true, but for you guys, because you only do cubic functions, this is always true. The point of inflection is where the second derivative is equal to 0. That's always true for the core maths people, so you don't have to stress about that. Okay, so this is pretty much what we're going to be looking at when we look at these graphs. Okay, so let's take a look at these graphs. So like I explained to you guys, drawing the graphs is not really all that important because they hardly ever ask it, just because it does take quite a bit of time to do it, and because it takes time to do it, they have to give quite a few marks for it, and they don't always have those marks available. Is there anybody who's struggling with drawing these graphs, the stuff that you did last week, or can I sort of skip it? I don't really want to spend time drawing the whole graph. Was there somebody who wants to see that? You struggle a bit. Okay, that's fine. We'll do one of those. Right, now quickly, let's just talk about increasing, decreasing. Okay, so in this particular example, they give us a function and they say the function f of x is equal to 2x cubed minus 3x squared minus 12x. Okay, so that's a cubic graph. And now what they've done here is instead of asking you to draw the graph, we're just quickly going to talk about a couple of basics, because this is just the basics that you need to understand in order to draw the graph. They asked, determine by calculation whether f is increasing or decreasing at certain values. So they've given you a couple of values. They've given you x is equal to -2. They've given you x is equal to 0. They've given you x is equal to -1. They've given you x is equal to 3. And they've given you x is equal to 2. And the question is the graph increasing or is the graph decreasing at those values? Now, the moment you hear the word increasing or decreasing, this is talking about gradients. This is talking about a positive gradient going up or negative gradient going down. So the moment you see this whole idea of the gradient, you have to remember it's about the first derivative. It's about the first derivative. So we have to find the first derivative in order to determine that increasing or decreasing. So I just go back to the original function and I say this is then going to be 6x squared minus 6x minus 12. Okay, now instead of entering all of these values individually, which is going to take us quite a while, I'm going to be a little bit lazy and I'm going to use my calculator, the table function, because that's what the table function does. The table function gives you the whole option to enter stuff. So I'm going to go to table function, but instead of entering fx, I'm going to enter the first derivative. Obviously, the calculator can't take the notation of first derivative. You just have to remember that I'm not entering the function fx, I'm actually entering the derivative function, the gradient function. So I'm going to enter that 6x squared minus 6x minus 12. And I'm going to start at the smallest value, which over here is -2. So I'm going to start at -2. And I'm going to end at the biggest value, which is 3. I'm going to end at 3. And I'm going to step in once just so all of these values can go in. So if you look at it, then you'll see here at -2, there we go, at -2, we have a value of 24. Now, because we entered that -2 into the gradient function, it's telling me for this particular function, fx, for this one, the gradient at -2 is 24. So that 24 tells you what the gradient is. So over here, my gradient is positive. It's increasing. It's going up at -2. Then if I look at -1, it tells me my gradient is 0. So if it's 0 right there, it's a stationary point right there, meaning the graph isn't increasing or decreasing. It's stationary. It's standing still. Then here at 0, I've got a negative value, -12, so it's a negative gradient, which means here the graph is decreasing. Then over there at 1, I've got -12, but they didn't really ask for 1. At 2, I've got 0 again. So there again, I've got a stationary point. And there at 3, I've got positive 24. So I've got an increasing function again. So when you have these values, you actually have a very good idea of what this graph looks like. Because if you organize these values from smallest to biggest, you say this graph is increasing, then it hits a stationary point, then it's decreasing, then it hits a stationary point, and then it's increasing again. So pretty much the graph looks like this. Increasing there, then it hits a stationary point, which is 0 over there, then it's decreasing over there, then it hits another stationary point, and then it's increasing over there. Let me just close the door. There's noise coming. Okay, so even though they didn't ask us to draw the graph, just looking at the derivative, so looking at the gradient, we already have a very good idea of what this graph looks like. Any questions about the idea of increasing and decreasing?
No.
Awesome. Right. Then, looking at the other basics, just the simple, straightforward basics, they then ask me about, well, yeah, let's quickly look at just if they ask me a question going, where's this graph increasing and where's this graph decreasing? Let's look at one of those. So they give me another example, and in this particular example, they say f of x is equal to -x cubed plus 6x squared minus 9x plus 3. So again, a cubic function. And what they ask here is they say, please calculate the coordinates of the stationary point. So they say, please calculate coordinates of the stationary points. Now, this is something you need to understand. The graph is stationary where the gradient is 0. So in order to find the stationary points, we have to set the gradient function equal to 0. So we need to set the first derivative equal to 0. So this is a rule. Whenever I want to find a stationary point, I find the first derivative and I set it equal to 0. So I take this function and I say that's minus 3x squared plus 12x minus 9, and I set that equal to 0. Now I'm going to divide everything by -3 just to make the factorization easier to do. Obviously, if you have a silver calculator, you can type that into your silver calculator and that will solve it for you as well. So it's really no big problem. So I'm going to take the -3, and then you've got x squared minus 4x plus 3 is equal to 0. And then I can throw that -3 away because it's really not important. So it's x minus 3 and x minus 1. So at x equal to 3 or at x equal to 1, we've got the stationary points. Now, very important, if they ask you for the coordinates of the stationary points, it's not enough just to give the x values. We've got to give the y values as well, because coordinates always come in pairs. So we have to have an x coordinate and we have to have a y coordinate. But when you want to find y coordinates, and this is very important, we always have to sub it back into the original function. Because if you sub that 3 back into the first derivative, all you're going to get is 0, because that's what the gradient is. And we don't want the gradient, we want the y coordinate. So there we're going to go and sub that 1 back into the original function as well. So again, a little bit lazy over here. I'm going to keep on working with the table function. We go back to the original one, and we say it's minus x cubed plus 6x squared minus 9x plus 3. And I'm going to just go from 1 to 3 because that'll give me all of them. So I start at 1, end at 3, step in 1s. Okay, so at 1, I've got -1, and please remember, don't get confused. I've now entered fx into this table function. I didn't enter the first derivative. So that means that -1, when it comes out, that's going to be my y coordinate. So that means this one's equal to -1. So it's the point 3, -1. That's the one stationary point or turning point. Then here at 3, they give me the value of 3. So that means the y value is 3. So this is the point 13, which is the other stationary point. So that's my stationary points. Now, a lot of the time what they do is they actually ask you, please determine the nature of these stationary points. In other words, one of them is a local maximum point and one of them is a local minimum point, depending on the shape of the graph. Now, if you watch the videos, I did show you that there are a couple of ways you can do this. One of the ways you can do this is you can actually just know what the standard form of this graph is, looking at this minus in front of x cubed. This is generally called my a value, but I also explained in the videos, we don't always call this the a value because sometimes they decide this coefficient of x squared is the a value and that coefficient of x is the b value. It just depends on the question. Okay, but if I look at the coefficient of the x cubed specifically, this indicates the shape of the graph. Now, the shape of the graph, you always go and you start from right going to left. So right to left, you start over here and you start like with one of those negative parabolas because of this minus. And then I just continue, that's going to be the shape of my graph. You can actually learn this. If this value in front of x cubed is positive, you can start on this side and you can actually do the positive parabola and then come down. Okay, so that is going to be your way. That's a bit better. That's going to be your way of determining it. Now, why is this important? Because the first point, the one with a smaller x value, is then in other words a local minimum based on this shape. And the second point, the one with a bigger x coordinate, is then a local maximum. That's one way to do it. That's one way to determine if it's a local maximum or minimum. The other way to determine, quite simply, is the following. And this, by the way, is one of the questions that they ask in this particular example. They say, please now go and work out where the graph is increasing and where the graph is decreasing. So let's do that one and then come back to these stationary points. So the one question is, where's the graph increasing? Now, increasing, again, that has to do with the first derivative because it has to do with the gradient. So that's where you have a positive gradient. Okay, so a positive gradient means we then want to know where is my first derivative positive or greater than 0. Okay, now I've got the first derivative over here, got it right over there, but careful people, don't use any version you've adjusted. Because remember, when you solve these stationary points, you did adjust by factorizing by maybe dividing by the -3, by maybe changing the signs. Why? Because it was an equation. But you always have to go back to the original one whenever you want to go talk about the increasing, decreasing. So I'm going to go back to this original one, which is minus 3x squared plus 12x minus 9 greater than 0. Now, this, by the way, obviously it's a quadratic inequality, so careful with your quadratic inequalities. I know we haven't done a lot of them since grade 11, but hopefully you can still remember. The first thing I'm going to do is I'm going to divide by -3. Now, careful, if you divide by a negative or you multiply by a negative, this sign needs to change. You've got to change the sign. This is then going to be x squared minus 4x plus 3. Now I'm going to factorize to get the critical values, which is then x and x minus 1 and minus 3. So my critical values is at 1 and at 3. I'm going to put them on the side here because a lot of the time people write down their critical values, and instead of writing down critical values, they write down x is equal to 1, x is equal to 3, which is wrong in an inequality. In an inequality, it's not equal to unless specifically it says somewhere there that it's equal to. Okay, so I'm just going to write down the critical values. It's at x equal to 1 and at x equal to 3. Now, a couple of ways you can do this. I know some of you just memorize it, and some of you can just write it down and go, oh, it's between 1 and 3. I know some of you can do that. I know some of you guys like to use the parabola, where you say this is 1, this is 3. I'm going to draw my parabola. And where is it negative? Below the line over here. So between 1 and 3. Some of you guys I know like the number lines. You put your critical value 1 there, you put your critical value 1 there, put your critical value 3 there, and then you just go positive, negative, positive, which again indicates the negative is between 1 and 3. So there's lots of different options to do that. Now, the good news at least is once you've determined where the graph is increasing, decreasing is actually quite easy to do, because decreasing is simply where the first derivative is then less than 0. So because it's where the first derivative is less than 0, I can then just go and I can take this one that I've already done all of that effort, and instead of saying, in this case, less than 0, I know that sounds a little bit weird because we started with greater than 0 and then we changed it over there. But whatever this one is, if I just flip it, it's going to be the other one. So that means I can then just say it's where x is less than 1 or where x is greater than 3. And this actually gives you, again, a very good idea of the graph. It tells you the graph is decreasing, then it is increasing, and then it's decreasing again. So it's decreasing, increasing, decreasing, which, by the way, we've already said. We've already said it over there. So all of these things are actually supporting each other. All of these things are actually helping. And then again, that means because we know the graph has the shape, we know the first stationary point is the local minimum, the second stationary point is the local maximum. We can also use the second derivatives to talk about the stationary points. So if I work out the second derivative, and again, I go back to this one, the original one, and I work from there. My second derivative is then going to be minus 6x plus 12. Now, to work out whether the points are local maximum or local minimum, I sub the x coordinate of the stationary point. The first one was 1, and the second one was 3. I sub that in there. Now, what you need to understand is you need to understand, and this is one thing that can get a little bit confusing. We start with the function fx. Fx, if you put an x coordinate into fx, you get a y coordinate out. That's what you get. Then you have a second function, which is the gradient function. So the gradient function, which is the first derivative of fx, if you put an x coordinate in there, you don't get a y coordinate out, you get the gradient out. Then you have the second derivative, which is another function. There, if you put an x coordinate in there, what you get out is you get an indication of the concavity. So you have to be very careful asking yourself, which one of the three functions am I working with? Am I working with first derivatives, gradients? Am I working with fx, y coordinates? Or am I working with second derivative, which talks about concavity? So in this case, I'm subbing into the second derivative. So whatever value I get out, I interpret it in terms of concavity. Okay, be very careful that you don't get confused there. So if I put the 1 in there, it's minus 6 times 1, which is minus 6, plus 12, which then gives you 6. Then if I put 3 in there, it's going to be minus 6 times 3, which is minus 18, plus 12, which is minus 6. Now, a positive second derivative means it's concave up. That's what it means. Whereas a negative second derivative means it's concave down. There we go. So concave up means the graph looks like this, because it's concave up. Concave down means the graph looks like that, which means it's concave down. So this, once again, is a local minimum because it's concave up. And this, once again, at 3, not the negative 6, that indicates the concavity. At 3, it's concave down, which means it's a local maximum. So you can use any of these methods to determine the nature of a stationary point, whether you use the gradient to indicate the nature of a stationary point, whether you indicate using the concavity, or whether you indicate just knowing what the shape of the graph is. The exercises that I gave you guys to do for homework, drawing those graphs, they did ask you with a stationary point to use the first derivative, which means working with a gradient. And it did ask you use the second derivative, which means working with concavity. So there were actually quite a few options there. Are there any questions about this, the whole idea of the stationary points? Anyone? Going?
No, ma'am.
Okay. Gone. Does that, so it makes sense? That's all I'm asking. Okay. Right. So let's then do an example of drawing it. I know it's spending some time on this, but like I said, if you understand drawing the graphs, then finding the equation of the graph is also fairly easy and straightforward. But let's look at one of them, which is drawing the graph. Let's see if I can find one. There we go. So in this example, it asks you, draw the graph, y is equal to minus x cubed plus x squared plus 5x plus 3. Now, whenever we're drawing graphs, we always have to remember there are certain points that they believe are very important. So if you don't put these points on the graph, you will get penalized. So when it comes to these polynomial functions, so your parabola and your cubic graphs, what you must always indicate, your x-intercept, your y-intercept, and your stationary points or your turning points. That is incredibly important. You have to do that. Now, in this case, we also have a point of inflection. Now, when you look at the point of inflection, that one you generally don't have to indicate unless they specifically ask for it. So you can get away with not showing the point of inflection, but if they say it. Bonga, do you have a question? Looks like your hand's up, or was that just my imagination?
Oh no, that's old. That's old. Sorry, that's old.
That's old. Okay, now that's absolutely fine. Like I say, just you're more than welcome to jump in at any time. Just unmute. I'd like some feedback. It's you have no idea how annoying it is trying to teach yourself and not knowing what you guys are thinking. So please just unmute and ask. Okay. So like I said, point of inflection, you can indicate it, but you don't have to unless it specifies. So just obviously be careful there. So I normally start with the stationary points. Don't have to start there, but stationary points. So stationary points, we find the first derivative, in this case dy over dx. Again, just my notation. Watch my notation because they give me y. I use dy over dx. So that's minus 3x squared plus 2x plus 5. Okay. We set that equal to 0, and I have spoken to you guys in the video. If you don't show that 0, they actually penalize you. Because a lot of people, they get a little bit lazy and then they just start solving an equation, which isn't actually an equation. If there's no 0 next to the equal sign, it's not an equation, so you can't actually solve it. So please, people, indicate, because there's a mark allocated for just that 0. Even if all of this is wrong, even if your derivative is wrong, even if your answers are wrong, if you just show that 0, you actually get a method mark. You get a point for that. So please don't forget. Okay, so I'm going to just go and I'm going to use, let's just write this out, minus 3x squared plus 2x plus 5. So I'm super lazy. I'm just going to use my silver calculator to solve that for me. So I'm going to change it to equation mode, which is my quadratic equation. So minus 3 is my A value, 2 is my B value. And then 5 is my C value. So it gives me 5 over 3. There we go. X is equal to 5 over 3. Or X is equal to -1. There we go. And please remember, it's not enough to get the X coordinate of the stationary point. We also need to get the Y coordinate. So to get Y, I'm just going to substitute that in there. By the way, you don't really have to show it. You can actually just go and say, let's sub that in. So you're going to say it's minus 5 over 3 cubed. And please remember, I put it into the original function because I need a Y coordinate. If I accidentally put that 5 over 3 into the first derivative, I'm not going to get the Y coordinate, I'm going to get the gradient, which is 0. So be very careful that you don't make that mistake. Sub it into the original for Y coordinates. Then we go plus 5 over 3 squared plus 5 times 5 over 3. And then plus 3. My Y coordinate there, they give me a really strange Y coordinate. You can see it says 256 over 27. Press the SE button and just round it off to 1 decimal place, because otherwise you're not really going to know where that is on the graph. So 9,5. So let's just go 9,5. Okay, so this is the 0.5 over 3, which if you do press it on your calculator, it's pretty much going to be 1 2/3. So 1 2/3 is going to be 1,7 if you round it off to 1 decimal place. 9,5, that's the first turning point. And then for this one, I put -1 in. And you'll notice I haven't cleared the screen, because I can then go and I can just go back and I can delete all of these 5 over 3s and then just substitute with -1, which makes it slightly faster. It's -1. And there's -1. Okay, so then I end up with 0. So that's the point -1, 0. Now, this is quite nice sometimes. And the reason this is nice is if you find a stationary point that is also on the x-axis, then you know not only is this a stationary point, it's also an x-intercept. So when you start finding the x-intercepts, you can just check and see that the values that you got here correlates with the values that you got for x-intercepts. Okay, so it's also an x-intercept, which is quite useful to know. Right. Now, I work on my x-intercepts, and to get x-intercepts, we always say y equal to 0, so I solve this equation. Again, people show the 0. So I'm going to say minus x cubed plus x squared plus 5x plus 3 equal to 0. Okay, I'm assuming all of you have the silver calculator, because we did have this discussion in that chat on polynomials. So we were talking about that whole idea of what do you call it, the factor theorem. So when we spoke about the factor theorem on how to solve cubic equations, I showed you how to do this manually. Now, I also said you don't really have to be able to do these manually unless you're writing your NBTs. Okay, so if you are writing your NBTs, no calculators allowed, and then you have to be able to solve this manually. But in your exam, just grab your calculator, change it again to equation mode, but now specifically number 4, because we're looking at a cubic equation. So A is my coefficient.
Wait, ma'am?
Yes.
For the NBTs, are we actually going to have to solve cubics without a calculator?
You could have to, yeah. You could. They ask quite a bit of stuff on functions, I know, for the NBTs. I don't think they'll give you difficult ones, because remember, what you generally do is you do inspection, where you sub 1 there, for instance, and if you sub 1 in there, you'll actually get 0, and then you'll know it's that.
Yeah.
Now, another way to know what your answers are is this. You see this one right there. We said this one is also an x-intercept. Now, if something is an x-intercept as well as a stationary point, and I did speak to you guys about that, about drawing the graphs, we can actually use this value twice when factorizing this. So let me just show this to you quickly, just for interest's sake. If I divide everything by -1, just to make that front value positive, which just makes the entire factorization easier to do, then it's going to be x cubed minus x squared minus 5x minus 3 is equal to 0. Now, because of this, that -1, which is my stationary point, I can immediately do this. Now, I can put that x plus 1. Now, be careful, because of the x value of the stationary point is -1. You guys have to remember this has to go x minus -1. And because it has to go x minus -1, I've got to change it to x plus 1. That's the first reason. That's why this is negative and this one's positive. Now, the second reason, the second thing is that square. That square only happens when an x-intercept is also a stationary point. And the reason that happens is because normally when the graph cuts, it cuts once, twice, 3 times. So that's 1, 2, 3 x-intercepts. But if that x-intercept is a stationary point, then the graph actually looks like this. Just to be slightly more accurate, I think it's going to look like this. There. So it cuts here, but there, the point which is also the stationary point, it pretty much bounces on the graph. That's what's happening. And because it bounces on the graph, this x-intercept counts twice. And because it counts twice, you use the bracket squared. That is a very, very important conclusion, and it actually helps you a great deal over here. That's why, because you know this is an x-intercept and a stationary point, you know it's one of the answers, and you can actually use it twice. Are there any questions on this?
No, I get it.
Okay.
I think.
Okay. Now, the nice thing about this is then, we just need to figure out this last little one, that last little stationary point. And to figure out that last little stationary point, I'm just going to go and do one little thing. I'm going to just expand this and say it's x squared plus 2x plus 1. And there's a good reason for that. Okay, here we go. Because you should know that the first term here multiplied by the first term there, that's a quadratic, and this is linear. So this one times this one has got to be equal to this one. So x squared times x is equal to x cubed. And this one times this one, this is the constant value, times the constant value here, it's got to be equal to this one. So 1 times -3. So then I know that this bracket is x minus 3, which then means I know my x-intercept is then x equal to -1 from here, which I already knew from here, or x equal to 3 from there. Now again, people, if you're writing a core maths exam paper, this whole discussion is really not necessary. I can go back to what I was doing on the calculator, which is just solve this particular equation right there. So this one, okay? And I can then just go and I can say it is -1 is my A value. No, it's doing this. Sorry. Can you guys see this lovely yellow thing on the... Okay, somebody's doing that. That's funny. Somebody did that and I went like, huh? Okay. -1 over there. We've got 1 over there. We've got 5 and then we've got 3. And now look what happens. The first value we get is 3. Look. There, 3. You see, all of these things are connected. So I know some of you guys, if I explain too much, you get a little bit confused. I completely get that. But actually, understanding all of this stuff makes it easier to do, because then you know that if your calculator is broken or you don't have a silver calculator, you're writing the NVTs, you've got lots of different ways to do it, if you can understand what's going on. And then the other one is if x equal to -1, which also I'm not surprised, I already got it up over here. Okay, so those are my x-intercepts. The y-intercept is the easiest one to do, because that will just be, if I set all of the x's equal to 0, so if I make all of these x's equal to 0, I end up only with 3. My y-intercept is 3, that's always going to be the constant value. Okay, so that's pretty much it. Now, if they don't ask you to classify the nature of the stationary point, meaning they don't really need you to go and do a second derivative test to see if it's local maximum, or do a first derivative test to see if it's local minimum, if they have no questions about that specifically, then you really don't need to go and do those derivative tests. You can just simply go back to the original equation over here, and like I said, if this value there is negative, you start very careful, please guys, don't get this wrong. You go from right to left. So you start right and you start with a negative parabola, that frowning face parabola, and then you just continue with a curve. that's the shape of this graph. Okay, so that's the shape of the graph. So now I know the shape of the graph. Because I know the shape of the graph, I actually don't have to go and do anything specifically there. Okay. Okay, so drawing the graph, let's just get a fresh piece of paper. Now, I did explain you don't specifically have to go and use the same scale that you do on the x-axis, on the y-axis. It just depends on you. There's sometimes you get these y-coordinates that's like 36. So if it's going to be 36, then you really don't have to go up 1, 2, 3, 4, 5. You can rather go up and say 6, 12, 18, 24. You can use whichever scale is more comfortable to you guys. So I need these points, which is at 1, 2, 3, and then -1, -2. And then my y coordinates go all the way up to 9. So I'm just going to make it slightly smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a little bit better. Okay. So my stationary point is going to be at 1, 7, 9, 5. So 1, 7 is round about there, and then 9, 5 is round about there. So that's the first one. Then it's going to be at -1, 0. So -1, 0 is over there. So that means I know the graph is going to have that shape because we discussed it over there. So I know this is actually then going to be a local maximum, and this one's going to be a local minimum. So I actually know that shape. So I don't really need to do a second derivative test. Then my x-intercept is at -1, which I've already got there, and at 3, which is over there. And then I've got my y-intercept, which is at the point 0, 3. So 1, 2, 3 over there. So I'm just going to put in the coordinates because you guys should know that if it's not on the axes, you've got to make sure that you put the coordinates in properly. So that's 1, 7, 9, 5. That's going to be a 3 because it's on the axis. You can just say 3. This is at -1, and this one is also at 3. Okay. And then I can just go up from there, turn over there, and then turn over there. Like I said, it doesn't have to be a piece of art. This one is pretty wonky, as you guys can see, but they're perfectly happy with that. If they did ask you for the point of inflection, then obviously you would have to calculate the point of inflection, but you can see it'll be halfway between these two. So when you work out the point of inflection, just for interest's sake, if I go back to this one, which is my first derivative, then I'm going to change that to -6x plus 2 equal to 0. So that's my second derivative equal to 0, which then means I've got 2 equal to 6x. And if I divide both sides by 6, x is equal to 2 over 6, which is a third. And by the way, if you go and you take these two x coordinates, these ones, that 5 over 3 and that -1. So if I say 5 over 3 plus -1, which is then -1, and I divide that by 2, you're always going to get the point of inflection. The point of inflection is always the midpoint. The x-coordinate is the midpoint of those two stationary points. Okay, so if you did want to indicate, you can just then indicate. Obviously, I don't have the y-coordinate there, but you can get the y-coordinate by simply subbing the 1 over 3 into the original. Okay, any questions on drawing these graphs? Going?
No.
Awesome.
Gone.
Like I said, that's pretty much what you need to do. Now,
Wait,
more
ma'am.
important, yeah, what was their question?
Yeah. So do we only have to put the amplitude, like the peaks, basically the peaks and
Yeah, remember this isn't really amplitude. Amplitude refers to a trig graph where there is what they call periodicity, meaning the graph repeats. Understand? So we don't really have amplitudes here. Don't confuse your trigonometric graphs with these graphs, because I know it looks like a trigonometric graph, but remember, trigonometric graph will make a wave, and then that wave will continue. This one doesn't. This one goes up, and this one goes down. And there's not, technically speaking, real symmetry in the sense that you can fold them over each other or anything like that. So don't confuse that periodicity of trig graphs with this. Okay. And that point of inflection, that's not really what you would call your amplitude. That's not really what we're looking at that. So that whole idea of amplitude, throw it away for these graphs completely. Don't even refer to it as amplitude. These graphs don't have an amplitude.
Okay, so if you only write down the peaks.
Point of inflection. Yeah, you write down
Okay.
the stationary points, which is your turning points in this case. You write down those.
Yeah.
So these are incredibly important. And you write down your intercepts with the axes. That point right there, the point of inflection, you only need to show that if they require it. Okay.
Okay.
Okay, awesome. Right, so let's look at finding the equation of these graphs. Now, I did do 2 videos, so you had 2 different sections on how to find the equation of a graph if the graph is drawn. Let's just see if I can find an example here. Okay, yes. Okay, in this particular example that they give you, it's not going to be very pretty. I'll give you pertinent stuff. So they give me all 3 of the x-intercepts. They say this x-intercept is -1. They say this x-intercept is 2. They say this x-intercept is 3. And then they give me a point over here, which is the point 112. Now, it might look like it's the point of inflection, but please remember, unless they state it's the point of inflection, you can't make any assumptions. So if they tell you it's a point of inflection, great. But if they don't tell you it's a point of inflection, the only thing you know for a fact is it's a point on the graph. So they didn't give you information about that. They just asked you, please find the equation of this graph in the form y is equal to ax cubed plus bx squared plus cx plus d. Now, again, when I was discussing finding the equations of these graphs, I did mention to you guys, a lot of the time, they actually give you the a value. So a lot of the time, you should please read the instructions very carefully, because the instructions might actually say, find the graph of y is equal to x cubed plus ax squared plus bx plus c. So the reason there wasn't an a in front of the x cubed is because they, technically speaking, they already gave you the value of a. So they tell you the graph is the graph x cubed, it means the coefficient of x cubed is 1. But that's where it gets a little bit confusing, because now instead of saying this is the a value, they call the coefficient of x squared the a value. So please, just whatever they call it, you have to use their reference to it. You can't go back to what we generally use. Okay. So in this case, they didn't give you the coefficient of x cubed, so we have to work it out. Now, first things first. The moment you have all of the x-intercepts, and this method only works if you have all of the x-intercepts, you write this down. Now, you should know this one from the parabolas. Remember, when you were finding the equations of parabolas, you had it like this. That was finding the equation of a parabola if you had all of the x-intercepts yet again. You can't just have one of them, you have to have all of them. Now, by the way, sometimes what they do is they give you one x-intercept, and then the other x-intercept is that turning point that I've spoken about. So the moment the other x-intercept is a turning point, all you have to do is use it twice. So instead of using it once in the one bracket, use it in 2 brackets if the x-intercept is also a turning point. Okay, so in this case, we're going to say y is equal to a. My first x-intercept is -1, so that's going to be x minus -1, so it's +1. Then it's going to be x minus 2, and then it's going to be x minus 3. Now, in order to find that a value, I use the other point, that point of 112. And I say, when the y coordinate is 12, so when y is equal to 12, my x coordinate is 1. So I put 1 in there. So this is then going to be equal to 2 times -1 times -2. So this is then going to be 2 times -2 times -1, so that's going to be +4. And if I divide both sides by 4, then my a value is equal to 3. So now I've got my a value. So now, in order to get all of that, I need to sub this back into that one right there. And yes, I'm unfortunately have to going to multiply all of that out. We don't really have any other option here. We're going to say y is equal to 3 times, and I'm already going to do the multiplication, maybe just of those second 2. So I'm going to just leave the x plus 1 over here. And I'm going to multiply that x minus 2 by x minus 3. So that's going to be x squared minus 5x plus 6. And then I'm going to leave the 3 out there for now. I'm going to multiply this out. So x times x squared is x cubed. X times negative 5x is minus 5x squared. And then plus 6x. And then I have to multiply 1 by x squared. So it's x squared. 1 by minus 5x is minus 5x. And 1 by 6 is plus 6. There we go. And then I can finally multiply the 3 in there. So 3 times x cubed is 3x cubed. Then I am going to just add these like terms together. So I'm going to go minus 5x squared plus x squared is minus 4x squared times 3 is minus 12x squared. And then over there I've got 6x minus 5x, which is x times 3, which is plus 3x. And then lastly I've got 6 times 3, which is 18. So now I can finally go and say, so A is 3, B is negative 12, C is 3, and D is 18. Because please remember to read the question. The question could just say, find the equation of the graph, and then you can stop over there. Or the equation can go and say, find the values of A, B, C, and D, which means you have to write that down. You have to answer the questions. You have to go all the way to them. Any questions on this one? Going? Okay, good.
No, we're good.
I'm going to do another one of these ones. Like I said, we could always do a session tomorrow. I'm not exactly sure. What does the timetable say for maths tomorrow? What time are we on?
Oh, I can check for you, ma'am.
Yeah, please check for me and let me know. Because then we ran a little bit short on time. Then tomorrow I can talk about finding the equation of a cubic function if the stationary points are given instead of the x-intercepts. And then I can also talk about the stuff you're going to have to watch today, because the video I put up for today is a little bit confusing. So if you do get to the video I put up today, it's called the graph of the derivative. I think there might actually be some questions about that tomorrow. So maybe we should just schedule one more lesson. Okay. Right. So.
Okay, thank you, ma'am. Ma'am, it says we have maths first thing tomorrow morning.
So that's at what, 8:30?
I think so, yes.
Okay.
It is 8:30, yes.
8:30 to 9:30.
Yeah.
Okay, so I'll schedule for 8:30 to 9:30, just so we can go over the last little section about these cubic graphs. And then I might also have to schedule one for Thursday just to go about the maximizing the optimization problems, but we'll talk about that tomorrow. Okay, so I'll send you guys an invite again for this one. Right. Oh, by the way, is it okay if I put the Zoom invites on the Google Classroom instead of sending you all an email, or do you prefer the email?
I think the Google Classroom is easier.
Okay, I'll put it on the Google Classroom because you can just copy that link. It's easy enough. Okay, right.
Yeah.
So in this particular example, let's see if we can finish this before we run out of time. They give me this point over there, which is the point -2, and they give me this point over there, which is point 1. So no, they didn't give me 3 x-intercepts like the previous example. They gave me 2. But remember this one, because it's also a turning point, we're going to use that one twice. Got it. So whenever it's a turning point as well as an x-intercept, we use it twice. And besides, we've got all the x-intercepts. Now they've also given me another point there, which is the point -3, 4. There we go. So we can again go and say y is equal to a times x plus 2, because remember you have to go x minus -2, so it becomes x plus 2. And we're going to square that because it's also a stationary point. And then we've got x minus 1 right there. Okay. Then we're going to use that other point to get the a value. So I'm going to say y is equal to 4 if x is equal to -3. Okay. So this is then going to be -1 squared, which is then going to be +1. And this one's going to be -4. So a is being multiplied by -4. So if I divide both sides by -4, a is equal to -1. Now, by the way, I didn't say this with the previous example, but if you look at the shape of this graph, you will know -1 is the correct answer, because look at the shape. When you go from right to left, as you draw it, you start with that negative parabola before you go up. So it actually makes sense that my a value is negative. So I know I'm doing something right. So again, I just sub it back into this. So y is equal to a, which is -1. I'm going to move that x minus 1 to the front, because this is actually pretty easy to quickly square. So that's going to be x squared plus 4x plus 4. So this is going to be x cubed, but if I multiply by negative, it's negative x cubed. This one's going to be plus 4x squared minus 1x. So it's plus 4x squared minus 1x squared, which is going to be plus 3x squared, but if I multiply by negative, it's minus 3x squared. I know I'm rushing a bit, but I've got an HOD meeting at 12, so I just want to finish this example. Then the next one, if you multiply x by 4, I get 4x. Now if I multiply negative 1 by negative 4, I get plus 4x minus 4x, which is actually 0. Okay, so I don't have to write that down. Now if I multiply these last two, minus 1 by 4, it's minus 4 times minus 1 is plus 4. So that means my A value is negative 1, my B value is negative 3, my C value is 0, my D value is 4. There we go. So that's pretty much trying to find the equation of the graph of all the x-intercepts are given. So what I will do then tomorrow, I'll put the invitation on the Google Classroom, and I'll discuss the ones where they don't give you all the x-intercepts. They give you x-intercept maybe, but they give you stationary points, points of inflection. Those ones are slightly more complicated because those ones involve simultaneous equations, mostly. So yeah, we'll definitely look at those ones tomorrow. And if you watch the video for today, you might have some questions about the graphs of the derivatives. Okay. Thank you so much for joining me again.
Thank you, ma'am.
Thanks. You need to tell me if this is useful or if you need more information or just feedback is welcome, guys.
It was definitely useful. Thanks so much,
Very
ma'am.
useful, ma'am.
It's an absolute pleasure. Stay safe, you guys. And I don't know, if you feel like you're thanks. If you feel like you're going crazy, just I don't know, go outside and scream for a bit. I'm sure that will help a little bit.
Maybe,
Thank you, ma'am.
ma'am.
Cheers,
Thanks,
guys.
ma'am.
Thank you. Bye.
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 What's up, Ponga?
Wow.
Wow, what, Ponga?